Hello, my name is Florent Privet. I'm a postdoc at Aarhus University, and I will talking today to this tutorial video about how to compute polygenic score using LDpred2. And this video was made for the PGC day at the WCPG 2021. So if you go to this tutorial of LDpred2, then I explain how to do the whole computation using some small data. So actually, if you don't have enough data to make your own LD reference, so actually at least 2,000 individuals, then we provide in the LDpred2 paper, we provide some LD reference based on the UK biobank, so on very large sample size that you can use. And here you can see the variants that are used in this data. And basically, this is a bit more than 1 million AppMap3 variants, where you have the information like chromosome position, alleles. You have also some pre-computed LD score. And also you have, we changed the position to different builds. So if you want to match with different, if your SumStat, for example, SumStat have different builds for the position, then you can match directly using those. Okay, so so this is the LD reference that we provide. So in this tutorial, we just use some small fake data, just of the purpose of not to have to download like large files and also to run it quickly. So you can download this tutorial data and zip it, and it will have a directory called TMP data. And then I just read the data from the BET format, the Plink BET format, in the format that is used in the big snipper package. So this format is easy. It's just a list with basically 3 elements. The first one is the genotype matrix, which is stored using a special format that is a matrix format, but stored on disk. And then you have 2 data frames, one with information on the individuals, and one with information on the genetic variants. I also read the summary statistic. So again, it's a fake summary statistic. So here I'm using only 50,000 genetic variants, just to make it small and easy to run. And actually, the data that we need to run LDpred2, so we need the effect size, beta, the standard error of the effect size, and also the sample size. So if you have the sample size per variant, then it's better. And also we need like the information, chromosome position and alleles to match between your summary statistic and the data that you're using. So just for the purpose of this tutorial, we just split the data that we have. So only like 500 people. We split in validation set and test set. So the validation set will be used to tune the hyperparameter, so choosing the hyperparameter with the best prediction, and the test set is used to just see how it works in the final prediction in the test set. Okay, the first thing that we need to do is matching the genotype data that we use with the summary statistic, so we can match by chromosome position and alleles. So to do that, there is this function called Snip Match. And actually, if you run this, you will see that basically almost no variant is matched. So the problem here is that the SumStats and the data is not in the position are not in the same build. So yeah, actually what you can do is modify the build using liftover and this function. You can, if you use the LD reference that we provide, you can use one of the other columns for the position in different builds. or you can, instead of joining by positions, you can join by the RSIDs. So for simplicity, we'll do that here. So now you can see that much more, many more variants are matched. Okay, now that we have matched the variants, we need also some LD reference. So you can, either use the LD reference that we provide or just compute one from your data. In LDpred2, we recommend to use a window size of 3 centimorgan. So you need to get the genetic position in this, in centimorgan. So for that, you can use this function. Just to convert the position, the physical position into a genetic position. Just for simplicity here, I've pre-computed them, and you can just get them from this field. And then per chromosome, we compute the correlation using this Snip function, using a 3 centimorgan window with this genetic position. And in parallel, it should be quite fast. And then from this correlation matrix, which is just a standard sparse R matrix, we can get the LD scores, because we'll need the LD score to run LD score regression later. So again, if you're using the LD reference that we provide some pre-computed LD scores. But remember that if you're using LD score regression with this LD scores, you need to use the number of variants corresponding to this LD score, so this total here, not a subset of the matched variants. So be aware of that. And actually, I convert this matrix into another sparse matrix format, but that is stored on disk. Just to make it more efficient to parallelize over this LD reference. This compact equals true is quite new. It's make just the matrix twice as efficient. So now, if you use the AppMap3 variants, the size of this data on this should be approximately 15 or 16 gigabytes of just gigabytes. And so you need to be able to store this, to keep it in cache so that it's fast. And you need also to store all the results from all the outputs from LDpred2. So if you're using like 50 or 60 gigabytes, it should be more than enough normally. And then we can run many models. So first, the infinitesimal model, which is just a model assuming that all the variants are causal, and actually there is an analytical formula for that. So it's just a matter of solving a linear system. So it should be quite fast. So you get the effect size, then you can get the prediction by just product with the genotype matrix, and then looked at the correlation between the prediction and the actual phenotype in the test set, and we get like 32% of correlation. Then we can run LDpred2 grid, which is then, so that there are two hyperparameters, the irritability, the SNP irritability, and the proportion of causal variant P, which can be smaller than 1, if you expect not all variants to be causal. So for the irritability, we use so the irritability estimate from LD score regression here. And actually, because LD score regression can be not very precise when, for example, the trait that you're interested in is not very polygenic. So we also try 0.7 times this value and 1.4 times this value. And actually, we also test 0.3 times this value because in a recent preprint, we'll see that if we use a small irritability estimate, it induces more shrinkage, more regularization, and it's sometimes useful when the quality of the summary statistic is not that great. For P, so a sequence between 10 to the power of -5 to 1 on the log scale. And then we have this parameter sparse. And if you use sparse equal true, it will just make sure that you have some effects that are exactly 0 to make the final prediction sparse. So lots of some of the effect size will be exactly 0, so the variant won't be used in the model. So we can compute the betas corresponding to all these models. So a lot of models that are running in parallel, then get the prediction from all these models. And then in the validation set, we can compute some kind of score. So here we use the t-score from a linear regression between the phenotype and the polygenic score. So actually you can use some covariates here as well. And if you're using a binary trait, then you can use a GLM with a family called binomial. And then we can look at all the models using ggplot if we want. So we have like the heritability, the color heritability, x-axis is the proportion of causal variance. This is the z-score that we get here, and sparse equals false or sparse equals no. We can look at the best models. So actually, if you care about sparsity, then you can maybe choose these models that is getting you almost the same score in the validation as the best model, but then you have like a very sparse vector of effect size at the end. We can get the best prediction, and then for the best prediction, we compute in the validation set, we compute the final prediction in the test set and look at the correlation with the phenotype, and then we get some much better prediction than the infinite model. So with LDpred2, it's usually the case that you would get much better prediction with LDpred2 grid compared to LDpred2 Inf. And then we have LDpred2 auto, which is so instead of trying many values for the hyperparameters, it just like estimate them from the data. So the heritability, Snip heritability, and proportion of causal variance are estimated directly from the data. We run actually many models here as well because we run many chains with different initial p-values for p. So in parallel again, so you get like here 30 different models. You can look at one of them where you get like the betas, the proportion of being causal per variant, the p estimate, the H2, the Snip heritability estimates, and so on. You can look at them in ggplot2, like it's the path of the each iteration, the values of each iteration in the Gibbs sampler. And then you can get all the prediction, and then you should have a way to filter the chains that, for example, didn't converge or diverge. So to do that, we propose two methods. So the first one is based on just computing the standard deviation of the predictors and just keeping the ones that are close to each other. Or you can also compare the heritability estimate and proportion of being causal estimates and look at the chains that are close to each other. And then the final prediction is just the average over the chains that you keep. And then if we look at the correlation with the final estimates, final prediction with the phenotype, that you get a very good prediction. And finally, I will talk very quickly about Lysosome 2, which is just a re-implementation of Lysosome, but that uses the exact same parameters as LDpred2, so this LD matrix and this beta SC and effect sizes. No, so effect sizes, standard error of effect sizes, and sample sizes. And so you can just run Lysosome 2 like this with the exact same parameters, then compute. So for a grid of hyperparameters, there are two hyperparameters in Lysosome. You would get all the prediction. Then you can choose the best one, again, based on the validation set. You can look at all of them. You can choose the best one. And actually what you could do is just, take the run LDpred2 grid, run Lysosome 2, and take the prediction, the best prediction overall in the validation set. Yeah, that's all.